Hi, everyone. Welcome to Thursday on Techstrong Gang. We've got a lot to go over. I mentioned IBM's new commercial-grade quantum computers. They're all shiny and silvery from the pictures. But we've got to discuss that. We've got some Cisco news and some cyber news on this bedbox botnet. Interesting stuff. But first, let me introduce you to our lineup of gang members for today that we're going to be discussing this with. First of all, sporting a shiny new haircut, looking good out there in the Valley. He's our Valley editor, John Swartz. Hey, John, how are you?
I'm good. Welcome back. I haven't talked to you for a while. I hope you had a great time in Italy. And it's good to be here.
Good. You know, there's something to be said about Tuscany. But we'll discuss that another time. John, welcome. It's good to see you. Next is our cyber beat reporter, one and only Terri Robinson. Hey, Terri, how are you?
Good. How are you? I'm completely jealous you were in Italy, but
I don't blame you, but I did come home kicking and screaming, but they got me home. And then from our neighbor up north, runs the, well, I don't know if she would, I think she runs the Canadian DevOps community as well as a bunch of other stuff. Garima Bajpai. Hi, Garima. It's good to see you, and it's great to have you here on the gang.
Hello, everyone, and great to be back here.
And then last but not least, our favorite Yankee fan, Mike Vizar, Chief Content Officer here at Techstrong. Hey, Mike, how's it going?
I'm good. I'm in Midtown Manhattan today in a hotel directly across the street from Madison Square Garden, otherwise known as the crime scene.
As the crime, well, you're still talking about your Knicks?
Knicks, yeah.
Yeah. I wouldn't have fired Tom, but whatever. I think there's a Dolan curse on the Knicks and Rangers.
Really?
You know, he's like bad luck schleprock. As long as he's involved, I don't know if we'll ever get anything done here. Anyway, let's talk tech. So Mike, IBM unveiled these big, shiny, honking, stainless steel looking boxes for commercial grade quantum computing.
Yeah, or at least something that is a drawing of a box that they're going to build, because it's not going to show up till 2029. But here's what they're saying. But here's what they are saying, and it's kind of interesting on two levels. One is they're saying that, they've kind of solved this issue where it's now an engineering problem rather than a computer science theory. And they think that they're going to actually build these quantum machines. And the two things that they're also saying is that the mechanisms for harnessing qubits and the software and the coding that they created wasn't going to work because it would require processors that were just too large, and it wouldn't scale, and it would be too cumbersome and too costly. So they basically went back to the drawing board, and they're saying we redesign the way the code is going to be created so that we can have smaller processors that will drive this quantum capability, and that'll enable us to build this amazing machine. They're going to have some proof of concepts and some testing machines between now and 2029 with an idea of creating something they're calling the Starling system. And that will be housed in a data center that they are building specifically for this in Poughkeepsie, New York.
Yay for Poughkeepsie.
Yeah, yay for Poughkeepsie. And, for those of you who do not know, it's, Poughkeepsie is in Westchester County, and, that's home turf for IBM. So, rather than building this thing in some other obscure place, they're essentially putting this in their own backyard. So I assume that they're very serious about it as a result. And they got some money probably from the state and the feds to do it. But Alan, you've been following this space. What's your take on it? Because the other side of this coin is they're saying that, the other methodologies that people have been talking about won't scale, and they were throwing some shade too.
Yeah, they were. Well, so here fundamentally, here's the issue, and they're not wrong, Mike. We've been hearing now for 4 or 5 years that in order for quantum computing to become real, I think the magic line was at 1,000 qubits or something like that. We had to have 1,000 qubits or 2,000 qubits. And we've seen the qubits go from 10 to 20 to 40. I think we've got maybe 100 200 qubit processors that are possible now, but not near 1,000. And so, the goalposts were pretty far out there. We were going to need some sort of material physics breakthrough to really achieve thousands of qubits, right? Or it was going to take a really long time. And we've had some kind of exotic solutions proposed, right? Microsoft inventing a different form of matter, whether you buy into that or not. Google has their Willow architecture, but still Willow was not going to get you to this level of commercial availability. And then recently, an interesting thing, much like when we first went to Linux supercomputers, right? How did we get those Linux supercomputers? We put a lot of machines together in parallel, right? So a Linux supercomputer really had literally hundreds, if not thousands, of Linux cores running. And from what I understand, it's a similar thing here. They figured out how to run these relatively lower qubit quantum processors in parallel. And so you have sort of that quantum supercomputer, if you will, if we can call it that. It's what I'm calling it. I'm sure there's a real term. And that's what this is about. Now, in doing that, this is like cloud native stuff where you got to go to microservices architecture. You need now to have your quantum software be able to run multi-thread in a parallel processing type of thing. And we're not even sure, prior to this, a big problem with quantum software was separating out the software calls that would need to be done on the quantum side of the house versus other processing tasks that would need to be done in a conventional bits and bytes type of processor. And and how do you separate that, then bring it back together into something that works for you? Now we're adding another level of complexity, which is I need to separate out the quantum from the non-quantum. Then I need to put that quantum into a serial type of, microservices, multi-threaded architecture to use a parallel processing, then bring that back together. And then we still got to join it up with what comes out of the regular processor. This is not a simple thing, right? Let's be clear. However, this is, to IBM's credit, a path forward in reality that may get this, as they say, by 2029 in good old Poughkeepsie. We'll see. I'm sure others will go down this path too before they have to resort to, inventing new forms of matter and energy and defying the laws of physics. The other thing is bully on IBM, right? They've been leading the quantum computing charge for a long time when it really was pie in the sky. And, you look at the history of IBM, Watson was AI before we knew AI, what it would do or could do, right? IBM has taken the lead in so many, from PCs to so many things and then they just kind of stood by and watched others claim the rewards and the glory and fame. I'd love to see IBM take the lead in quantum. They deserve it.
Garima, when I was listening to the press conference for this, the thing that crossed my mind, to Alan's point about the complexity, I was like, so is there going to be like a compiler and an SDK for this, or how am I going to actually program to this thing? And what's your take on this as you kind of look at all this?
So, as Ellen said, that it's a double-edged sword, right? So it has opportunities and threats. So opportunities, definitely it will help us, solve complex problems which couldn't be solved by the limitation of the hardware, right, and the processors. But on the other side, it's also creating opportunities for the software professional, because if you think about in advanced engineering and the scalability of a modular architecture, I, there is a lot of action on the software open source as well as DevOps community. Alan mentioned quantum software. I would also mention quantum DevOps, because I want to kind of get this into the mix. This will create a large set of revolution or evolution in that software and DevOps space. I mean, interoperability, for example, becomes a big thing as well, because there is traditional ecosystem of quantum technology as well as the advanced engineering techniques. How do you make it work? Then there is SDK toolkit. There are several toolkits available, for example, from Azure, from Amazon, but there will be new toolkits required for this kind of a modular architecture. And this whole claim is unsubstantiated right now, right? So we'll have to prove it from a software practitioner's perspective. If you think about scaling it and industrializing it and commoditizing it for general purpose needs, I think there is a lot of action needed from a software professional. The entire set of CI/CD pipelines, the DevOps tooling, observability, error correction, and auditing of error corrections and all that needs to be kind of in place at quantum engineering scale, right? So there's a lot of action for software practitioners to kind of lean into and look at it from a different perspective altogether.
And one of the things they keep talking about is the comparison to classical computers. It's not like development of classical computers is going to be at a standstill for the next 4 years. So we will see them get faster too. So it'll be interesting to see what use cases actually lend themselves.
Right. That's the key. I don't think it's a question of speed of classical computers versus quantum computers. I think what we've got to remember is quantum computing, at least as we understand it now, solves some very specific use case problems a lot exponentially faster than classic computing ever will. Right? That's the bottom line. There are some things like encryption is a great example, right? We could brute force 512-bit encryption if you had some sort of monster machine, and for all we know, the NSA does. But it'll still take months, years, whatever, to brute force that break that encryption. Where by the very nature of quantum, it can be done very quickly, relatively speaking, right? You're talking years and decades versus minutes. So that's a great use case for it. But I don't know, other things I've heard, weather forecasting. Another great potential use for quantum computing, because just the amount of variables in there make it such. But we don't really have, what are the other killer apps for quantum? What are the other killer use cases for quantum?
There's tons of stuff in the field of chemistry that will lend itself to quantum. Because when you think about quantum, and what they're saying is that they're trying to mirror the way nature computes and the way that nature pulls these things together, and we haven't cracked that particular code, and that's what they're trying to do. And so there are probably lots of use cases that will lend themselves to quantum. But I guess I keep pointing them, the quantum people keep obsessing about what they can do versus classical computers. And the thing about the classical computers is they too get faster. And a lot of times so far, every time quantum said we could do something that classical couldn't do, the classical guys showed up 6 months later and said, here's our new processor that can do those things slightly faster or with much capability. But to your point, I think it is going to be a hybrid, right? It's going to be, when even IBM is talking about using high performance computing alongside quantum to kind of go build an application. So it will be a set of microservices that you're invoking and calling on a quantum to run specific classes of workloads alongside a classical computer. And that's how that feels to me, at least. But there is another aspect of this thing that I wanted to bring Terri in People have been talking about Q Day for a while. Q Day is when we're allegedly going to break all these encryption schemes. And I guess what IBM is kind of saying here is that will happen no later than 2029. And it might happen sooner still, but at least we have some sort of date that says that those encryption codes are most likely going to be cracked starting in 2029 or sooner.
I don't know how solid that date is, but I mean, that's what, if they're going to do this by 2029, then I guess that's it. Or at least it gives us something to fixate on right now. The best advice right there too is to start preparing for that. Don't just wait till 2029, to see if it happens. I think that is the biggest concern probably with quantum is that encryption will be broken. And we talked about this a couple of weeks ago, I think, when we were talking about prime numbers, right? Not being as random as we thought. And really the idea there, though, is that quantum was going to pose a bigger issue when it comes to.
Yeah. But we have quantum proofs theoretically, from what NIST tells us. We have quantum proof algorithms. DigiCert and many of the other certificate providers have already incorporated that. That may turn out to be a big Y2K thing as far as I'm concerned this Q Day. What may be more troubling is all of these bad guys who are sitting on tar balls full of hashed personal information that they've not been able to crack to date, and now using quantum, if they had access to quantum, they'd be able to crack it. But of course, that information goes stale over time too. So the longer that, if you wait till 2029, a good chunk of that's going to be useless anyway.
I think it's going to be an issue, though. And I think, you're right, Alan, because NIST is on the case, right? They've been working on this. And it's not like people are sitting still, but I really think you need to, as an organization, maybe start looking at what this might mean.
Yeah, no, you got to make sure. Have you adopted quantum proof certificates? How often are you changing your certificates? Where are where is your encryption? What data is encrypted and what encryption you're using? Yeah.
Yeah, and be sure to keep your security audits and everything and risk assessments on point. You're going to have to be constantly vigilant, I think. But all that's hygiene anyway.
John Schwartz, what's your assessment that the Chinese come up with a quantum computer that's similar to this sooner?
Yeah, that's likely, probably. Can I just interject a bit of skepticism into this, because I like to do that. 2029 is a long way away. By the time we reach this date to have a fault-tolerant quantum computer, the Summer Olympics in LA will have come and gone. We may have a new president. Hopes, unless we change that. I'm just thinking that I bully to IBM for getting our attention, for being at the forefront of something again. I am a huge fan. My dad worked at IBM for 20 years. He was an engineer. They were the leader up through the 70s, 80s, even into partially the 90s. I do laud them for what they're trying to do, and I think it's really cool. And I think it's great that we're talking about this. But a lot of things are going to have to happen between now and then. And I think about this within the context of what happened this week. Remember Monday, Apple had the WWDC. A year after they announced their big Apple Intelligence, we're still kind of stuck in the mud. And I'm thinking later today, we're going to have Tesla talk about the robo-taxis, which we've been hearing about for years. So I think sometimes it's important to kind of step back and look at the achievability. I actually asked a couple of people about what IBM was up to, and they said they don't even know what's going to be happening in 2026, let alone 2029. So I just wanted to say that. But again, going back to this whole discussion, bully for them for doing something that's exciting on the cutting edge, and for being a little bit arrogant. And they need more arrogance. They've been missing it. They've been missing their swagger. So I do compliment them for that.
after many decades of swagger, I agree with that. They are definitely missing it. I actually worked on an IBM account in a brief stint at an ad agency many years ago, and one of the guys, and they were starting to get a little whipped by some of the other companies that were out there that were a little sexier. The technology was a little more appealing, at least on the surface. And this guy just looked at me with a woebegone expression and said, why can't we get the love? Why can't people, see what great things we do? And I'm like, you know, I felt a little bad for him, but I also wasn't his therapist. But, I think it's nice for IBM to kind of get that swagger back and maybe well
Well,
deserved.
they have a whole wing of their inventions at the Computer History Museum in Mountain View. I mean, literally, a section is devoted to IBM. You know what? The irony of history is that Apple, if they're not careful, they're going to start getting into that IBM kind of conversation where they're kind of an afterthought. I'm not. The half life of the Apple products is pretty long, but there's more and more attention being paid to what they don't do and what they're not doing well. And that's something that every tech company goes through inevitably.
So let me end this. Let me end this segment with this right here. You know what that is? The smallest violin in the world playing Hearts and Flowers. Because all those people complaining about IBM, all the people I know who've worked at IBM and are sitting on IBM stock are doing pretty damn good. The IBM stock you could look at it short term, but over the long term, their IBM stock has seen them through. And the same goes for Apple. Poor Apple, just a couple of $1 trillion cap. So, talk about first world problems. Let's take a break here on Techstrong Gang. We'll come back. We're going to talk more first world problems. Cisco. You're watching Techstrong Gang.